Here I want to show that the Maclaurin series for my function actually converges to the function for all x. So I have my function f of x is e to the negative 2x. My first derivative, so n is 1, right, is negative 2 times e to the negative 2x. My second derivative is negative 2 times negative 2 e to the negative 2x. My third derivative, negative 2, negative 2, negative 2, e to the negative 2x. So we see a pattern here. So my nth is negative 2 to the nth power times e to the negative 2x. So I want to bring out my negative 1. So I have negative 1 to the nth power times 2 to the nth e to the negative 2x. But remember, when I want to look at the remainder, because the remainder is what I'm interested in. So let's first look at our series, and then we'll look at our remainder. So my f of x, right, is which is e to the negative 2x. Well, what are these all evaluated at 0? Well, f of 0, that's 1. F prime of 0, well, that's negative 2 times 1, so it's negative 2. So it's really just the sum from 0 to infinity of what my coefficient is, because this is always going to be 1. So I have negative 1 to the n times 2 to the n, and then it's x to the n, and it's all over n factorial. So I want to use Taylor's theorem and look at my remainder. So let's remember that my n plus first derivative, because I'm going to be using that, is negative 2 to the n plus 1, or negative 1 to the n plus 1, right? E to the negative 2x. So for Taylor's theorem, I know that my remainder, which is greater than 0, has to be equals, the nth derivative evaluated at some z. So I have f of n plus 1 at some z over n plus 1 factorial, and I'm looking at that term. And so that equals, remember that was negative 2 to the n plus 1 e to the negative 2x, and that's f at z, right, over n plus 1 factorial times x to the n plus 1, because I don't know what my x is. Before it was, remember we were plugging in 0, but now I'm looking at it. So we're not going to look at we're going to remove that e to the negative 2x because it doesn't have an n in it. So as n gets bigger, it's going to stay the same. It's not going to change anything. So I'm really just going to look at my limit as n goes to infinity of negative 2 to the n plus 1, x to the n plus 1 over n plus 1 factorial. And so again, I'm looking at my coefficient, so I'm going to look at the parts that have I want to looking for my n. So but if I look at my limit as n goes to infinity of 2, I bring my x in, 2x to n plus 1, if I bring that inside, over n plus 1 factorial. Remember, the negative, if it's absolute value, goes away. And I know as x gets really big, this is going to go to 0. I mean, as n gets really big, this is going to go to 0 because the bottom's going to get really big. So I know that my remainder is going to 0 as n goes to infinity. So since the remainder is going to 0, so that's the difference, right? The error, since the error is going to 0, it converges. It converges for all